Welcome to the deep dive. Today, we're really getting into the nuts and bolts, opening up some pretty astonishing technical blueprints. We're looking past the grand strategy of things like Mulberry Harbours.
No, we're going tactical, deeply tactical.
Exactly. We're diving into the operational notes for what they called flexible sea bridging equipment, stuff designed for the heat of the moment.
It's really a look into the sheer audacity of the logistics involved. I mean, picture this. You've just landed on a hostile beach, maybe under fire, and the priority isn't just digging in.
No, it's building a highway immediately.
Right. A high-capacity road stretching thousands of feet out into open, often rough water. And it needed to be built, well, basically instantly, and handle tanks, heavy ones.
That's the core mission we're exploring today, the mechanics that made it even conceivable. This equipment, its primary design goal, was rapid unloading of big ships right onto those freshly captured beaches.
Specifically connecting the messy shoreline to something more stable, like those spud pontoon pierheads we've maybe touched on before.
And the whole design philosophy, reading these documents, it's fascinating. It wasn't about brute force rigidity.
No, not at all. They called it a semi-rigid structure. The engineers, they were smart enough to know you don't face the ocean head-on if you can help it.
So they designed it to kind of roll with the punches.
Pretty much. The idea was it functions like a long, flexible chain yielding to the sea's movement. The notes actually state it was usable without artificial protection, like breakwaters, in almost anything except the absolute worst storms.
Which is incredible confidence when you think about the loads involved.
Yeah.
And the documents mention two main types, right?
That's correct. There was the MKI equipment that was rated for 25-ton loading, good enough for tanks at the time, provided they kept, a decent spacing. About 80 feet apart, the manual says.
But then there was the upgrade. If they needed serious heavy lifting capability, right away.
Then they brought out the MKI, significantly beefier, this one, rated for 40-ton loads. 40 tons.
Okay, and here's the detail that really jumped out at me, buried in the technical notes. It speaks volumes about the precision.
Go on.
It says that if the moorings were tensioned correctly, and we definitely need to unpack how they did, that a cruiser tank could cross this floating, flexible bridge at speeds up to 40 miles per hour.
40 miles per hour on a structure designed to move with the waves. Yeah, it's astonishing.
It really elevates it from just a temporary fix to a high-speed military artery, doesn't it?
Absolutely. It tells you every single component, every connection, every mooring line had to be engineered and assembled perfectly to handle that kind of stress.
So our deep dive today is all about those technical reference notes. We're going to try and uncover these hidden engineering marvels and maybe appreciate the sheer logistical ballet required to make a 40-mile-per-hour flexible bridge a reality.
Okay, let's break it down. The fundamental building block.
Right, the core roadway itself, those 80-foot spans and the floats holding them up.
So the standard setup is a series of these 80-foot spans connected end to end. They carried a heavy-duty steel deck, 10 feet wide.
10 feet. Enough for a tank or a truck, but not a lot of room for error, I imagine.
No, definitely not. Precision driving required, I'd guess. But the real cleverness, or maybe the complexity, is how they linked these spans. It wasn't just a simple pin joint.
No, the ends were specialized.
Yeah.
They had these box ends coded W1 and W2.
Exactly. W1 always faced the shore, W2 always faced the sea. And the key bit, architecturally speaking, is that the W1 end of the next span actually seats inside the W2 end of the span already laid.
Ah, like nesting boxes. A very deliberate fit.
Very deliberate. It's the first step towards handling that movement. On land, you build a bridge, you want it rock solid, rigid.
But out at sea...
Out at sea, rigidity is your enemy. It leads to stress fractures. So you need controlled movement. And that movement comes from this system of internal linkages, mostly these things called cable springs.
Cable springs. Okay, these sound important. W36 and W37 in the manuals?
They are the heart of the flexibility. They run right through those nested box ends, connecting the span to the bearing seatings on the float below. They ensure the whole thing acts like that long, flexible chain. The wave lifts afloat. The springs allow the joint to articulate rather than snap.
And the assembly instructions here are incredibly specific, even color-coded.
Yes. The W37 spring is painted RE, apparently very important. And these weren't just off-the-shelf cables. They were pre-stretched and precision drilled. And the notes are emphatic about something called the long leg.
Okay, why does the long leg matter so much? What is that?
Well, if you look at the diagram, each spring assembly seems to have two links or legs. The manual mandates, it really stresses this, the long leg must be positioned on the outside in the sheave, the pulley mechanism.
And if you get it wrong,
Right.
if some poor squatty puts the long leg on the inside,
The springs won't seat correctly, they won't align properly in the mechanism, and that leads directly, the manual warns, to overstressing the entire joint.
which, when that 40-ton tank hits it at speed,
It becomes a catastrophic failure point waiting to happen.
yeah. It's a perfect example of a tiny assembly detail potentially having massive battlefield consequences. Get the long leg wrong, the bridge fails sooner.
Incredible. So controlled flexibility depends utterly on following those precise, maybe even fiddly assembly steps.
Right.
Okay, so the joints allow movement. What's holding them up? The bridge floats.
Right, the foundation.
Right.
And these aren't just simple pontoons. They were designed hydrodynamically. The shape was meant to cause minimal disturbance in rough seas, basically to cut through the waves rather than be tossed around.
And they needed to be towable easily.
Yeah, towable from any direction, which simplifies getting them into position in what must have been a chaotic environment.
Two main types again.
Steel first.
Yep, the steel floats were the standard lighter option, relatively shallow draft, about 4'7" when supporting two spans. Because they were lighter, they were fitted with these big hardwood bumpers.
Bumpers. Against what?
Against the span itself, slamming down onto the float in heavy waves. The manual calls it pounding. Imagine the shock load. Those bumpers were there to absorb some of that brutal impact. They weighed 16 to 20 tons each.
Okay, so steel for standard use, but for heavy duty.
For the MKC, or just for more stability, they had the concrete floats, nicknamed the Beetle.
Beetle, because of the shape.
Possibly. Or just the sheer weight. These were serious bits of kit. Two sizes, PP6 for MKI bridges, and the really big PP7 for the MK6. We're talking 45 to 55 tons.
Wow, so much heavier. Deeper draft, too.
Oh yeah, about 1.3 feet deeper than the steel ones. That extra mass gives them a lot more stability, makes them less prone to being bounced around.
But if the float is that massive and stable, how does that fit with the flexible chain idea? Doesn't that risk jarring the connection to the span?
Good question. They thought of that. The connection wasn't metal on metal rigid. The steel transoms, the beams fastening the bridge structure down onto the concrete float.
Yeah.
They didn't bolt directly. They passed through a special assembly. It involved a thick pad of hardwood, which was then capped with a steel liner.
Ah, so the hardwood acts like a giant shock absorber.
Exactly. A calculated shock absorber. It allows just that tiny bit of give or compliance needed when a huge wave hits, preventing the massive, relatively unmoving concrete float from transferring a sudden sharp shock up into the steel span above and potentially fracturing it.
It's a really elegant balance, isn't it? Rigidity in the span for the load, mass in the float for stability, and then these clever mechanical interfaces, the springs, the hardwood packs, to introduce just the right amount of flexibility.
Precisely. It's systems engineering, really, applied to a very dynamic problem.
Okay, so we've got the basic structure. But the real magic seems to lie in the components designed to cope with the realities of the ocean and the battlefield.
Which brings us squarely to the star player in flexibility, the telescopic span, the gap adjuster.
The gap adjuster, I like that. Tell us about it.
Structurally, it looks pretty similar to a standard 80-foot span, but the key difference is a sliding center section, like a trombone almost.
Allowing it to change length.
Exactly. It gives a really crucial 9 feet of movement range. It could be closed up tight at 71 feet 3 inches or extended right out to 80 feet 3 inches.
9 feet of adjustment per telescopic unit. That sounds like a lot. Why so much?
Tides. The relentless rise and fall of the sea. That's the big enemy here.
Right, because the distance from the fixed pierhead out at sea to the point where the ramp touches the beach changes constantly.
Massively, especially when you consider the difference between neap tides when the tidal range is smallest and spring tides when it's largest. That difference alone could be several feet of water level change.
And that changes how far up the beach the ramp needs to sit.
Precisely. The telescopic span is the component that absorbs that difference. It takes up the slack or pays it out as the tide changes, keeping the connection to the shore viable.
Were there specific rules about where you put these in the bridge chain?
Oh yes, very firm rule in the manual. You never coupled a telescopic span directly to another telescopic span.
Why not?
Presumably for structural stability, you don't want a whole section of bridge that's potentially sliding. They had to be placed between two standard fixed-length spans. Their job was purely adjustment, not primary structure over a long length.
Makes sense. But given the loads, Remember that 40-ton tank moving this sliding section, especially starting it moving? That must have taken some force.
Immense force. The tests they did on the MKI version are quite revealing. To get the telescopic section moving from a standstill took a load of 25 tons.
25 tons just to overcome the static friction.
Exactly. Once it was sliding, it was easier. Only about 12 tons needed to keep it moving. But that initial breakaway force is huge.
Which puts a massive emphasis on keeping those sliding parts moving freely, especially with salt, spray, and grit getting everywhere.
Which is why the manual has this very clear, almost stern maintenance note. The sliding box top and bottom cords must be, and they use the phrase, well greased before assembly.
And the consequence if you don't.
The manual spells it out. Time loss in the field of operations. And in that context, under fire, trying to get supplies ashore, time loss wasn't just inconvenient, it was potentially fatal to the mission. So, grease those slides.
A simple instruction with huge implications.
Yeah.
Okay, besides the mid-pier adjusters, there were also specialized end units, right? For connecting the whole floating road to the fixed pier head.
Yes, the telescopic ND spans. These were slightly different again, used only for that connection to a solid structure like a spud pontoon.
What was different about them?
Critically, they used the W2 box, ends the seaward type, at both ends of the span. This allowed them to connect to the next key component for alignment.
Which was?
The pivot plate, W80 in the parts list. This is the bit that deals with the messy reality of trying to connect a long, drifting structure to a fixed point in moving water.
Because even the best tugboat skipper isn't going to get 1,000 feet of floating bridge perfectly lined up, right?
Not a chance. Especially not quickly. So the pivot plate gave them some crucial wiggle room. It allowed for 6 degrees of misalignment out of squareness, they called it, on either side of the ideal center line.
6 degrees. That doesn't sound like much, but I guess at the end of a long pier.
It's enough. Enough so the crew doesn't waste precious minutes or even hours trying to achieve perfect millimeter alignment in choppy seas and possibly under pressure. They could connect quickly, securely, even if it wasn't perfectly straight.
But surely there's a catch. You can't just have the whole bridge snaking around, can you?
There is a catch. While that pivot plate allows the final connection to be off by 6 degrees, the manual warns strongly about the rest of the pier. You could physically bend the whole line of spans into a gentle curve, large radius. But if you did, the engineers calculated you had to accept a 50% reduction in the bridge's overall load-bearing strength. Half.
Ouch. So for maximum efficiency, for that 40-ton capacity, you really needed to keep the main run of the pier as straight as possible?
Exactly. It's a classic engineering trade-off. The pivot plate gives you speed and forgiveness at the connection point, but overall structural integrity demands you aim for straightness along the main length.
Okay, so before any of this connection could happen, these big sections had to get to the site. How are they transported? The towing links.
Right. Back at assembly depots, probably somewhere safer, they'd pre-assemble sections of the roadway, usually 4, 5, or maybe 6 spans linked together. These were called towing links.
And towing a 400-foot chain of flexible spans across potentially rough water must have been tricky. How did they keep them stable?
With a clever temporary addition, steering vanes. Part number W74A.
What were they? Like rudders?
Sort of, but much simpler. Basically, large timber structures bolted temporarily onto the main girders at the rear end of the towing link. They were lowered just enough into the water to provide directional stability, like the fletching on an arrow. Stop the whole thing snaking uncontrollably behind the tug.
Clever. And temporary, you said.
Completely. As soon as the link arrived at the erection site, the instructions were to cut them loose and discard them. Get rid of them quickly.
Why discard them? Wouldn't they still be useful?
Because during the fine maneuvering needed for coupling the links together, those vanes would just get in the way. They were designed purely for the long-distance tow, then jettisoned. Smart, disposable engineering.
And that level of pre-assembly must have drastically simplified things on site.
Oh, absolutely. Imagine trying to bolt together individual 80-foot spans in the middle of the ocean. Pre-assembling them into larger links was essential for achieving the speed required, because the whole name of the game was lightning-fast erection.
Which brings us to coupling these huge multi-span links together at sea. How on earth did they lift and align these massive, heavy structures?
With another piece of quite brilliant, specialized temporary kit, the erection tank, W92.
An erection tank? Sounds impressive. What was it?
It was basically a large cylindrical steel tank, weighed 56 tons empty. Its one and only job was to lift the end of an incoming span about 2 feet higher than its final position.
2 feet higher. Why?
To give clearance, remember those nesting W1 and W2 box ends and the cable springs? You needed to lift the incoming W1 end clear of the receiving W2 end so you could maneuver the couplings and pins into place without the colossal weight of the span resting on them. That 2-foot lift provided the necessary working space.
Okay, controlling the buoyancy of a 56-ton steel cylinder precisely enough for that kind of lift must have been tricky. How did they manage the water ballast?
It was divided into 4 separate watertight compartments inside. Flooding was controlled by 2 big hand wheels that operated sluice valves, letting water in. But, and this is a crucial detail, you couldn't just open the sluices.
Why not? What happens?
Air gets trapped inside the compartments. If you just open the water valves, the air has nowhere to go, so the tank only partially floods. It won't sink enough, won't provide the controlled lowering needed.
Ah, so you need to vent the air.
Exactly.
No.
There were 4 2-inch air cocks, 1 for each compartment. The manual is adamant. These must be open to let the air escape as the water floods in. That's how you get proper controlled flooding.
And for the final, delicate lowering part, settling that span down the last 2 feet.
Interestingly, the fine control wasn't done with the big water valves. You left those fully open. The final, precise rate of descent was managed by carefully adjusting those 2-inch air cocks, controlling how quickly the trapped air could escape.
That seems counterintuitive. You control the descent by letting air out, not by controlling water in.
It seems so, but it likely gave them much finer control over that last critical movement. Now, getting the water out again to raise the tank for the next lift, that was different.
How did they dewater it?
That needed help. A compressor truck had to drive out along the already completed bridge sections. It would hook up hoses to 4 smaller 3/4-inch air cocks on the tank. Pumping air in forced the water out.
And there was a danger here, too.
A big one. The manual explicitly warns against trying to flood the tank using only those small 3/4-inch air cocks.
Why would that be bad?
Because they were too small to allow the air to escape quickly enough as water potentially rushed in through leaky seals or the main valves, you risked over-flooding, losing buoyancy control completely, and sinking the entire 56-ton tank, which then becomes a major salvage job, losing critical time. Precision again, absolute precision required.
Okay, so the erection tank lifts the new span end 2 feet up. The existing span end is waiting. How do they guarantee they line up side to side, laterally, especially with wind and current pushing things around?
Another clever piece of guidance kit, the trumpet system, W84.
The trumpet system, like a musical instrument.
No, more like a giant adjustable funnel made of steel. It was hinged so it could move up and down with the erection tank, but it strictly controlled sideways movement.
And its job was to guide the incoming span.
Exactly. Specifically, it guided a component called the timber transom, W130, which was part of the incoming link's end structure. The trumpet effectively funneled this transom into the perfect lateral position,
Bringing the critical bearing points close enough together.
so the crew could relatively easily connect those vital cable springs. Final fine-tuning of the sideways position was done using tackles, ropes, and pulleys rigged to corner bollards on the floats. The instruction was to haul the timber transom right home into the trumpet.
And once it's aligned laterally and the springs are connected,
Then they start the controlled flooding of the erection tank using those 2-inch air cocks. The span gently lowers the final 2 feet, the W1 box settles into the W2 box, and the connection is made. Load bearing achieved.
wow, that is a complex sequence. And the documents keep hammering home the need for speed and careful timing. What kind of erection speed were they actually aiming for?
The target, with a well-trained crew and everything running smoothly, tugs, compressors, anchor teams, all doing their bit, was an astonishing 300 feet of bridge per hour.
300 feet an hour. That's, what, a mile of road in less than 18 hours while fighting the elements?
That was the goal. It demanded incredible coordination and also having every single tool, every spare part immediately to hand. No time to go searching.
Which probably explains the contents of that standard toolbox, the W149, that was apparently fastened to every towing link.
Exactly. It wasn't just a few wrenches. These lists usually show real operational foresight.
So what was in this essential toolbox?
All the specialized spanners needed for the unique fastenings, obviously. Things called relief wedges, W137 presumably to temporarily take the load off a bearing if you needed to swap something out under pressure. Spare parts for the cable springs, naturally.
Okay, standard spares. Anything unusual?
Oh, yes. The star item. A rocket pistol with lines and refills.
A rocket pistol. Like a flare gun, but for lines.
Yeah.
And a bridge construction toolbox.
Precisely. Think about it. What if the sea was too rough for the small boats to get close? What if the SLUG boat we'll get to that was unavailable or damaged? How do you pass the first crucial line, the messenger line, to the shore or to the next link?
You fire it across with a rocket pistol.
Exactly. It's contingency planning at its finest. A plan B for establishing that first connection, ensuring the operation could continue no matter what. It shows they planned for things going wrong, right down to the smallest detail.
Incredible foresight. Okay, so the spans are coupled. The roadway is structurally complete, but it's still just, well, floating there. It needs to be anchored securely. Laying the moorings.
A massive, critical job. Every single bridge float needed moorings both upstream and downstream to hold it steady against tide and current.
And these weren't lightweight ropes?
Definitely not. The standard mooring wires were serious business. 3¼ inch circumference, steel wire rope. They came in lengths of 12,270 feet.
Why so long?
To ensure enough length out to get a good angle and hold even in deep water, that length was rated sufficient for depths up to about 43 feet.
And these long, heavy wires weighing over a ton each came on big wooden drums, W53. How did they get a 1.25-ton drum plus the anchor itself underneath the bridge structure they just built? Because the spans hang quite low, don't they?
They do, which required another specialized piece of gear, the mooring shuttle. W166.
A shuttle. Like a space shuttle.
Huh, not quite. This was a very low-profile, flat-top dumb raft, often made mostly of plywood, apparently. Its key design feature was being low enough to slide under the bridge spans with minimal clearance.
And this shuttle carried the drum and the anchors.
Yep. It carried the big wire drum and 2 of the anchors used, which were called kite anchors.
Kite anchors, what were they like?
The kite anchor, W124B, was his specific design, weighed about 6.5 hundredweight, so roughly 730 pounds. But despite that relatively modest weight, it was tested to hold against a 20-ton pull.
20 tons? How?
The kite name probably refers to the shape designed to dig in quickly and efficiently, burying itself to get maximum holding power with minimal dragging across the seabed. On the shuttle, they were stored resting on hinged flaps on the bottom.
And release how?
Simply by cutting rope lashings holding the flaps closed. When the shuttle was in position, snip the ropes, the flaps drop open, and the anchor falls straight down.
Simple and effective. And there was a specific way the drum had to be loaded.
Yes, another one of those crucial details. The manual is very clear. The mooring drum must be loaded so the wire pays out downwards off the forward side of the shuttle.
Why forward?
So the wire pays out smoothly behind the shuttle as it moves into position, laying the wire flat on the seabed without tangles. Getting a kink in a wire rope under that kind of tension would weaken it dangerously. And they had a hand brake on the drum axle to control the payout speed, again, to prevent kinking.
Okay, so you have this low-profile shuttle with a massive drum and 2 heavy anchors. What pulls it under the bridge? You can't use a normal pug.
No. You use the wonderfully named SLUG boat.
SLUG boat, what does that stand for?
Surf landing, undergirder boat.
Undergirder, that says it all.
It really does. This was a unique little vessel, about 20 feet long, weighed maybe 2 tons, very shallow draft, powered by 2 Austin 8 HP engines.
2 small engines. Why 2?
Redundancy, probably. But also low-speed torque and maneuverability. You need precise control when you're towing a heavy raft under a steel structure that's moving up and down on the waves. It also had a 1-ton winch on board for handling the mooring lines once laid.
So its entire existence was dedicated to this one very specific, very hazardous task.
Absolutely. Its only job was to motor under those low-hanging bridge spans, towing the mooring shuttle behind it to position the anchors correctly. The manual actually instructs the 2-man crew to keep well down in the cockpit.
To avoid hitting their heads on the bridge girders.
Exactly. As the boat bobbed up and down, the cockpit was designed to be watertight, apparently ready to withstand glancing blows against the bridge structure in those incredibly tight, dangerous conditions.
Just amazing specialization. Okay, anchors are laid. Now back to that incredible 40-mile-per-hour tank crossing speed. You said it depended entirely on correct mooring tension.
Utterly non-negotiable. The moorings had to be pulled incredibly taut. The goal was to limit float surge. The sideways or back and forth movement of the bridge floats to an absolute minimum.
How did they know when the tension was right? Did they have tension meters?
Probably not practical in the field. They used a visual, surprisingly low-tech standard. The engineers figured out that the mooring wire was tensioned correctly when, at high water, the wire met the surface of the water about 20 feet out from the end of the float.
Ah, so they used the curve, the catenary of the wire itself, as a gauge. Simple, visual, field usable.
Exactly. And to achieve that specific curve, that precise degree of tautness, required pulling the wire with a 5 to 6 ton force.
5 or 6 tons. That's what it took to properly dig those kite anchors into the seabed and take all the slack out.
Right. And if you achieved that tension, the design worked. The float surge, even in pretty rough weather, was limited to about 10 inches. Just 10 inches of sideways slop.
10 inches. On a floating structure carrying tanks at 40 miles per hour, that's almost rigid.
It's incredibly tight tolerance. But if the moorings were left slack, if they didn't get that 5-ton pull, the surge would become excessive, the bridge would snake around, making high-speed crossings impossible and potentially wrenching the spans apart in bad weather. Tension was everything.
The precision at every stage is just staggering. It feels less like temporary construction and more like building, permanent infrastructure that just happens to float.
That was clearly the aim. Heavy-duty performance from a temporary system. And the designers knew that even with all this specialized kit, the real world would throw problems at them.
Like the environment itself. Let's talk about how they handled 2 big challenges mentioned in the notes. The huge tidal ranges and landing on rocky shores instead of nice sandy beaches.
Right, tidal range. We touched on it with the telescopic spans, but it's worth emphasizing the scale. The difference between neap tides, smallest range, and spring tides, largest range, could be 4 feet or even more in some locations.
Just to clarify for listeners, neaps are during quarter moons, springs during new and full moons.
That's right. And that 4-foot difference in high water level dramatically changes where the water's edge is on the beach, especially a gently sloping one.
So the distance the bridge needs to cover changes constantly. That's the telescopic span's job again?
Primarily, yes. That 9 feet of adjustment per unit becomes critical. The example calculation in the notes is for a 4,000-foot pier. The design recommended incorporating 8 telescopic spans along its length.
8 spans, 9 feet each.
Yeah.
That's 72 feet of total potential adjustment.
Exactly. And they calculated that on a fairly typical 1 in 15 slope beach, you'd need about 60 feet of that 72 feet just to cope with the difference between the highest spring tide and the lowest neap tide.
60 feet, just to stop a gap opening up between the end of the bridge and the usable part of the beach.
Right. Without that massive adjustment capability, the bridge would be unusable for chunks of the tidal cycle as water gaps appeared. The telescopic spans let the shore and ramp float be winched further up the beach at high tide or let out further down at low tide, keeping the connection continuous.
It's incredible foresight. Engineering the bridge to mechanically compensate for the moon's gravitational pull, essentially. Okay, what about the ground itself? What if it wasn't sand, but nasty, jagged rock?
That was a problem. Floating kit works best on soft ground, where the floats can bed down gently. On rock, especially jagged rock, you risk punching holes in the floats or having them sit unevenly.
So what was the solution for rocky foreshores?
They used the steel floats, not the concrete ones, fitted with special add-ons called rock inserts, W131 and W132. These inserts were designed to hold temporary legs, or spuds. They used standard V-trestle column units as these spuds.
So basically giving the float temporary feet. How did that help?
It allowed them to prepare the seabed. Here's the procedure. While the float was still floating in, say, 8 feet of water, just off the rocks, they'd lower these spuds down until they rested on the rock below.
So the bridge end is now supported on these legs off the bottom.
Exactly. It's temporarily grounded on the spuds, holding the float itself clear of the jagged rock. This crucial step gave access. Personnel could then get underneath the suspended float to examine the actual rocky berth where the float would eventually sit.
And prepare it.
Yes. They could use sandbags or even bags of cement mix to fill in holes, level off sharp points, basically create a custom-prepared, relatively flat bed before the float was allowed to ground directly onto the rock during the falling tide.
Wow. So they use the bridge itself as a temporary work platform to prepare its own foundation. That's incredibly resourceful.
Once the bed was prepared, they'd raise the spuds and let the float settle down onto the nice, smoother patch they'd just created.
Very clever. And mooring on rock needed something tougher than the kite anchors, presumably.
Absolutely. For a permanent or semi-permanent hold on rock, they couldn't rely on drag embedment anchors. They used the rock anchor, W158.
What was that?
It was essentially a large eye bolt designed to be grouted into a hole, drilled, or blasted into the rock.
How did they make the hole, especially underwater?
with a 10-pound beehive-shaped charge of explosive. The notes explicitly say this could be done underwater if necessary, very specialized work.
Okay, homemade, eye bolt placed. How do they grout it underwater quickly?
With a special quick-setting cement mix. The manual is specific. It would harden in just 10 to 15 minutes.
10 minutes, underwater.
Yep. And reach full structural strength in 24 hours. This allowed them to set incredibly strong, permanent mooring points very rapidly, even on the most difficult, solid rock seabeds.
The level of problem solving for every possible contingency is just remarkable.
Yeah.
Okay, we've covered the bridge itself. What about the business end? The pier heads where the ships actually unloaded.
Right, the interface. The LST pierhead was obviously critical, designed for those landing ship tank vessels. It was typically formed using two of the big spud pontoons, those stable platforms with legs connected together by one of those telescopic end spans, the Mk2 version for strength.
And the goal here was speed of unloading, maximum throughput.
Always. The design incorporated special buffer pontoons attached to the main pierhead. The LSTs could literally run their bow ramp right up onto these buffers,
allowing them to discharge
simultaneously from both decks. Vehicles could drive off the upper deck directly onto the pier, while tanks and heavier gear came out of the lower tank deck ramp onto the spud pontoon itself. The whole setup was wide enough for two LSTs to berth and unload side by side, double the speed.
Efficiency maximized. And finally, they even planned for the roads getting damaged.
They did. For the MT pierhead motor traffic, so mostly lorries, the manual suggested providing multiple roadways leading out to the pierhead. 3 is the number suggested.
Why 3 roads? Redundancy.
Partly redundancy, yes. If one road was damaged by enemy action or needed repairs, traffic could keep flowing on the others. But it was also about traffic flow. Lorries are slower than tanks, especially when heavily loaded. Having multiple lanes prevented bottlenecks forming at the pierhead itself, ensuring a better flow, as the manual puts it.
It seems every single aspect was thought through to maximize speed and resilience. If we try and picture the whole erection process happening, that 300 feet per hour pace, the coordination must have been intense.
Oh, absolutely staggering. Let's visualize just one coupling sequence, maybe mid-pier. You've got an incoming towing link, maybe 5 spans long, being maneuvered into position by a tug just to seaward of the existing pier end.
Okay, link arriving. What happens next?
Simultaneously, the SLUG boats have to be launched. Maybe they use the rocket pistol to get the first light messenger line across if conditions are bad. That line is used to haul across a heavier hauling line.
Which connect to one?
To the compressor truck, which is already sitting on the completed section of the pier. It hooks up maybe a 600-foot warp line and then drives back towards the shore, using its weight and engine power to winch the massive new link into approximate position.
While the truck is pulling, what else is happening?
The crew on the incoming link are frantically cutting loose and dumping those temporary timber steering vanes we talked about. They're just dead weight now. And crucially, the mooring operation for the new link begins almost immediately.
So the mooring shuttles get launched.
Exactly, loaded with their wire drums and kite anchors. The SLUG boats then start their incredibly dangerous job of towing these shuttles under the newly arrived, possibly still moving, bridge spans.
And they have to navigate around the mooring lines already laid for the previous span, right?
Precisely. This required careful timing. There were things called racking springs holding the completed spans tightly aligned. These had to be temporarily slacked off just at the moment the SLUG boat and its shuttle needed to pass underneath, near the joint.
So they loosen the existing structure momentarily.
Just enough for the SLUG boat to pass. Once it's clear, the new mooring wire laid by the shuttle is picked up, maybe using those same slacked springs to haul it on board, transferred to heavy deck stoppers, and then the tensioning begins, pulling it taut to that critical 5 or 6 ton load.
So picture this, a massive floating structure being winched by a truck, a tiny boat dodging underneath, anchors being dropped precisely, temporary legs being adjusted on some floats, specialized buoyancy tanks being flooded and vented to lift multi-ton spans by just 2 feet, all happening at the same time, against a ticking clock set by the tide.
And don't forget the main coupling operation with the erection tank and the trumpet system aligning the spans themselves. That could happen somewhat independently, but the whole sequence link, arrival, positioning, coupling, mooring, tensioning had to proceed almost concurrently, like a production line. The manual insists the value of speed and skillful maneuvering cannot be overestimated. Any delay in one step held up the entire 300 foot per hour process.
It really paints a picture. Achieving that level of intricate coordination, using all this highly specialized equipment, right down to the rocket pistols in the toolbox and the purpose-built SLUG boats, it demonstrates something fundamental, doesn't it?
It really does. It shows that winning a war based on logistics, especially in amphibious operations, wasn't just about grand plans. Success rested absolutely on mastering the smallest details, the finest engineering tolerances.
It was genuinely the difference between having that high-speed, 40-mile-per-hour military road functioning within hours or having just a tangled, useless wreck of steel drifting in the surf. Every single component we've discussed, the W1, W2 boxes, the hardwood packs, the red painted springs, was a specific answer to a specific dynamic high-stakes problem.
And solving those problems required not just clever design, but incredible execution.
So thinking about this deep dive into the blueprints, what does it all mean for you listening? You've heard about the staggering complexity, the layers upon layers of specialized engineering and procedural precision needed for what was essentially a temporary bridge.
I think the main takeaway is how that complexity scaled right down to the individual and the small team. This whole massive enterprise, this vital logistical artery, depended entirely on the fact that thousands of ordinary servicemen could learn and execute this incredibly difficult choreography perfectly, under immense pressure, at speed.
It wasn't just construction, it was almost performance art. Logistics elevated to an art form demanding extraordinary training.
Absolutely. And given how much the documents stress speed and careful timing, requiring this intricate dance between tugs, tiny SLUG boats dodging under girders, compressor trucks pulling, anchor teams hitting precise tensions, all while the tide is rising or falling, I mean, just pause and consider the sheer mental focus, the physical precision, the discipline required from those crews.
Performing this 300-foot-per-hour engineering ballet, often under the threat of attack.
Yeah.
What level of training, what kind of sheer human commitment must have been needed to make this complex blueprint a functional reality under the ultimate pressure?
It's humbling to think about, really, a level of dedication that perhaps defined that entire operational era.
Thank you for joining us on The Deep Dive. We'll see you next time.